Hello, in this video I'm exploring how Faraday's law creates magnetic braking. This lab demonstrates Faraday's law of induction. A changing magnetic field induces currents that create opposing fields. When I drop a magnet through the aluminum tube, it falls much slower than expected because induced currents create magnetic drag. In this experiment, our goals were to measure the fall time experimentally, model this computationally, and compare results to theory. Our tube was 46.5 centimeters tall, with 1.5 centimeter thick aluminum foil around a 2.3 centimeter cardboard core. The neodymium magnet was 2.5 centimeters tall. In 5 trials, we observed an average fall time of 1.25 seconds, which is far longer than the zero point 0.3 seconds predicted for freefall. In the first trial, the time was 1.2 seconds of falling. In the second trial, it took 1.4 seconds for the magnet to fall through the aluminum tube. And the third trial was 1.2 seconds. The fourth trial was 1.24 seconds. And the fifth trial was also 1.2 seconds for an average time of 1.25 seconds. We modeled the tube as stacked conductive rings. The key physics principles were Faraday's law, induced currents, Lenz's law, and force calculations via Biot-Savart law. Our assumptions were perfect cylindrical symmetry, uniform magnetic field, and negligible air resistance. Our simulation predicted 1.15 seconds versus the experimental 1.25 seconds. The 8% difference comes from tube imperfections, magnetic field simplification, and air resistance not being modeled. Both showed the expected terminal velocity behavior where magnetic drag balances gravity. Now to answer the what-if questions. For question 1, if resistivity approached zero like a superconductor, currents will persist indefinitely, completely stopping the magnet via perfect magnetic braking. For the second what-if question, cut-in holes will interrupt current paths, reducing braking. Our model assumes complete rings, so we see localized current disruptions around slots. In experiment 1, In experiments, I demonstrated how Faraday's law governs magnetic braking through quantitative experiments, computational modeling, and physics analysis of induced currents. These principles power real-world applications from eddy current brakes to maglev trains. Finally, I would like to acknowledge the resources and tools used in this experiment, including GlowScript for coding and the lab instructions provided by my course. Thank you for watching.